All right, welcome to Game Theory. I'm not going to try to be funny because it's a show about. It's not a podcast. I got all my interests from podcasts. Oh man. Okay. Anyway, this is Game Theory. Welcome everyone. So we're doing chapter 4. I need to write something down and just have something that I can say and default to because it's just been insane not having that.
We can tell our viewers to subscribe and get on audible.com and use an access code. Pretend like we're sponsored by Audible.
Okay, yes, we're sponsored by Audible, Gatorade, and Mountain Dew. I hate all. Well, Audible is evil. It's like you're renting space on their horrible network. Anyway, I don't. Oh man, rate us on iTunes. We're not on iTunes, but okay, YouTube. Thumbs up on YouTube. Okay, let's get to it. So we're doing chapter 4. Who read chapter 4? AKA Martin. Did you read chapter 4?
I must admit that I haven't really. So please spare your wisdom on us, Carl.
Well, I am happy to do so. In fact, last time you read chapter 3 and no one else was prepared, so it's my turn. So let me start sharing my screen because chapter 4 was surprisingly easy. Everyone's going to be happy because they'll probably learn something, but not have to think much. So that's nice. So chapter 4 is on game trees, introduction to game trees. And essentially what game trees are, I'm actually gonna skip a bunch of this stuff. This is a game tree. So the chapter is on sequential games. And let me actually get out my notes. I took a couple of them. And this is what they kind of look like. And I will explain. It's pretty simple what they actually do. So you can see my mouse, right? Okay, cool. So player 1 has the choice of going in this game. This game is very simple. It's just they either choose up, down, and then player 2 chooses left or right, right? So player 1 chooses up or down. And depending on what player 1 chooses, player 2 can either choose left or right. Pretty simple. And these are the actual payouts for the choices. And so what you can actually do is with these extended form games, I think is what it's called, extensive form games, you can actually turn them into normal games, just like we were seeing in our other chapters right here. So as you can see, this 2-1 corresponds to player 1 choosing up and then player 2 choosing left, which is right here. And then 1-2, it would be Bershmer. What is that? Oh, why is that a 2-1 and not a 3-2? It's very strange. Oh, I see. Okay, well, they have actually a description of all of the different choices for player 1, player 2. Anyway, I maybe they. Oh, here we go. Up, left, up, left, right. Well, I'm not doing a very good job of explaining this, but generally this should be correct.
So it seems like the strategies that are listed by player 2 are dependent on what player 1 is doing. So the left one is left if player 1 chooses up, and left if player 1 chooses down. And the left-right is left if player 1 chooses up, and right if player 2 chooses down.
Okay, wait. So left is say that one more time.
So left is the strategy of player 2 that regardless of whether player 1 chooses up or down, player 2 is going to choose left. And the second strategy, left-right, is choosing left if player 1 has chosen up, and choosing right if player 1 has chosen down.
Okay, I see. That makes sense. But then, and the payoff, if player, well, it shouldn't. Is that right? Because why is the payout 2-1?
Because player 1 has chosen up, and the response for player 2 to up is to choose left. So the first letter of what the strategy is called for player 2 is what player 2 will do in the case where player 1 chooses up. And the second layer is in the case where player 1 chooses down.
Okay, perfect. That makes sense. That is definitely correct. And so there's some important terms. So this is an example of a this is a sequential move game, right? So you see sequential moves. However, there's an alternative, which is simultaneous moves. So simultaneous moves, the important term to know around that is information set. So in this game, there's an information set right here. These are a member of the same information set, which means basically they have access to the same information from my understanding. What that entails is that the player 1 is going to choose up, or the player 1 is going to choose down. However, at these 2 points, they know the same thing, right? So they don't actually know if, did they choose up or did they choose down? Like they're not sure. And that's because they both basically share they're not privy to that information. So what that does to the actual game matrix is it makes it pretty, I mean, in this case, it's similar to what we've used, like all the games that we've been doing normally, just like player 1 is choosing something and player 2 chooses something, and they don't know, like they're just choosing simultaneously, right? Which is the kinds of games that we've been studying for a while. And so in this case, what Martin was talking about for the last game doesn't quite apply, and now it's just like straight up 2-1, 3-2, -2, -6-2, -1-4, right? And so you can see right here corresponds. Does that make sense?
Yeah, absolutely.
Cool. And so then the next part, essentially what this chapter does, well, we consider a prisoner's dilemma game, and essentially we show that even in a sequential setting, the prisoner's dilemma still holds. Because in a sequential setting, you can think about it where player 1 is either going to confess or not confess, and then player 2, it's always in their interest to confess once again. So if they don't confess, then player 2, I think 1 is confess, right? Yeah, 1 must be confessed, just judging by the points.
So the C is for confess, I think, also.
The C is for confess. Okay, that makes sense. Yeah, so if they don't confess, right, then player 2 has 6 points for confessing. If he does confess, then 2 points for confessing. And so that works for a sequential game. And we model it out the same way, just like Martin was saying, where you take into consideration the kinds of different strategies, depending on what they would choose. Now, this is the prisoner's dilemma with, two-stage prisoner's dilemma. Exactly. And this is where it I mean, these graphs, by the way, most of these, what they suggest using a tool called, what is the, Gambit? Not Gambit. Is it called? Oh, it is Gambit. Yeah. They suggest using a tool called Gambit. I wasn't actually able to check out that tool. I would have, oh man, I should have done a demo. I wish I had. It seems like it's very cool and it will solve these for us.
How can you find Gambit?
To be honest, I don't know. I can like look it up.
I can research that in the meantime.
Yeah, that'd be cool. Because I haven't actually checked it out yet. So if you notice, right, this is actually combining, or is it combining? No, this is, yeah, okay, so this is just two-stage prisoner's dilemma where the choices are simultaneous. Cool. We'll link that in the notes, the Gambit software. And so this is prisoner's dilemma where they don't know where it's simultaneous, and you know it's simultaneous because of these like information spaces or sets. I can't remember what it's called. Sets, yeah, information sets. So I didn't really go into that, but this is which one is this example? Spin fire. Oh, this is back to the Russian roulette game. Right, and so it doesn't really go into massive detail for the Russian roulette outside of just like, you know, providing the different payoffs. And this is, as you can see, a sequential game. But the most exciting part. Let me just go ahead. Wait, how do we reduce? Oh, this is, I think, how we reduce it to a strategic game. That's why I highlighted that. Here we go. So this is a good one. Okay, do you mind if I go to the poker one? Here we go. This is the best. So this is essentially explaining why this is an example where you have uncertainty, right? And why it's so important to be able to model players not having complete information. By the way, there is a term called, is it complete information? I don't know what it's called actually, damn it. But something along the lines of complete information. This one doesn't have complete information. And so player one chooses an ace or a two. So of course player one knows like what card they drew. Now they have the ability to either fold or place a bet. Now this is player two's move, right? So this is player one. I think I could be wrong about this, by the way. The numbers that I'm circling, I to be honest, didn't do a totally comprehensive job, so I'm still somewhat shaky. But player two doesn't know what card player one has, right? So they are going to be judging their information based on just whatever card they possibly could have. Actually, no, I think in this game it's just
connected.
Yeah. Why? Well, what were you gonna say actually?
I was wondering why the two were connected, because I thought that meant that they would make their move simultaneously. But now I realize that from player two point of view, the two games, or since player two doesn't know whether it's an ace or a two, those scenarios are the same. That's a nice modeling of information. Yeah, cool.
Exactly. That's right. So it basically means that I think in this game it's actually only an ace or a two. I think those are the two things that they model. They don't model like every card in the deck. So the player two knows it could either be an ace or a two, but the thing is they don't know which one, and that's why we have this information set, right? This is like the set of information available to these 2 points is the same, and that information is going to come from this, I think, or something like that, or I don't actually know. Um, I guess this. Yeah, that's something I'm not 100% sure on is like, if you're in the information set, how do you know what information is available? I guess it's, you just can't distinguish. Oh yeah, you can't distinguish between these two paths. That's what it is. So like you could be in this path or you could be in this path.
Yeah, and when you're forming your strategy, it can't be a factor in your strategy whether player one has an ace or a two, because that's not an information that will be available to you.
Exactly. So they're both of those paths lead to the same kind, or from the player two's perspective, they both could have been the reason why we're there. So this, and then the rest is kind of simple, right? You either call, in this case, if you call because they had an ace, you're going to, it'll be, well, let me just, let me see, where's the, yeah, so like, you will have the, why is it the same rewards? Oh, these are the reward. Schmer. You'd think that if they had an ace,
Mm-hmm.
and then they raised, and then player two raised, that the payout would be less.
But there's a different probability, right? After the raise, one is 1 in 4, and the other one is 1, 2, or is it?
I think that these are the probabilities at which you play the action. So this gets into mixed strategy, mixed strategies. So these are all like, I'm going to raise with 0 probability. Oh, that's why. That's why they're the same, because they're raising the same probability.
But at the next step, they're not the same, right?
Yeah, this is at the next step. I'm pretty sure it's back to player one. So if you notice at the next step, it's player one here. Right. I think that this is the thing for player one, that this one is player one and this two is player two. I basically underlined everything. I mean, do you mind if, should I clear this or?
No, it's pretty cool. But what was your question, Carl, originally?
Oh, my question was, so why is this? Oh, it's flipped. Okay, this is right then. This makes perfect sense. Because this is now going to be 3 points for player one because ace won. And this is going to be negative 3 points for player one because two lost. And it's going to be 3 points for player two because two lost for player two, but it won for player one. No, opposite. Two lost for player one and one for player two.
Yeah. But the strategies there, or the probabilities, are those the optimal strategies that are already written into the game?
Yeah, I think that they just gave us a model for this scenario. Okay. And we're basically just trying to learn we're just learning how to interpret these models.
Cool.
So this is, of course, like, it's an assumption that raising should be done with 0 probability, right? In both of these cases, raising is done with 0 probability. At least that's what it looks like to me. I could be wrong about that, but I think it's done with 0 probability, which means that these are actually never going to like come up from my interpretation of this graph, of this chart.
Yeah. Okay, that's interesting. That it would never be in player two's interest to raise.
Yeah, I mean, I think it's a lie. I think it's just like, I mean, this is not even really poker. This is actually just poker if you only have two cards, ace and two, and you have very particular payouts, right? And this is not even accounting for how much you're raising. I think it's a contrived example, but you can kind of visualize it, I think, a little better than the other examples. And I really like how it displays the information set, which is really a key term to understand.
Yeah, yeah, it looks like you're right that those are the probabilities and their optimal strategies. Cool. Interesting example.
Cool. So I'll move on unless we have more questions. Anything? Okay. I'm going to erase it, just FYI. Okay. Just doing it. Leroy. So it actually gets cut down to just this when you put it into what's it called? Gambit. Yeah. And so they just basically explain all of the strategies, but I think we went over that.
And I mean, in this chapter, we don't deal anything else with matrices. I mean, as soon as we have them in matrix form, we know how to solve them, basically. From
the previous chapter, exactly.
Cool.
Which is super nice. Like I'm loving the fact that we can just decompose it to what we already know and then like calculate. So here, this is essentially Greece versus Athens.
Nice.
And it's a contrived example, of course, not a real thing. But the idea is that the Persians, these are player one. Persians are player one. So I'm actually going to do this really carefully. So player one is the Persians. So that's player one, right? They have a 50% chance. Let me try. 50% chance to either climb or use the road. So these are two different paths that they can choose.
Is that not a choice that they can make? And then, it turns out that their optimal strategy will be to do it with 50% probability?
Yeah. Yeah, that's what I meant to say. I'm sorry. Okay. So those are the two choices, right? And what they do is before they go anywhere, they just flip a coin because they know that Greece knows what their stuff is, and so they figured it out, right? They know that they should just flip a coin.
Yeah, they just solved the game.
Yeah, exactly. They solved the game, so they figured it out. So, on the other hand, there's Greece, right? Here's Greece, player two. So now, if you see, this is part of the same information set. So what that means is that from Greece's perspective, both of these paths, they could have either climbed, they have to basically make, they're not going to know, they won't be able to make their choice after the Persians move their army, right? The Persians are going to move their army and they either have to wait in hiding they have to either attack them on the road or on the cliff, right? So they're going to have to make that choice, and that's why this is the same information set. So there's it's a simultaneous. That's what the way I'm trying to explain it is. It's a simultaneous choice. Like the same time that Persia decides to climb or go to the road, Greece decides to either defend the cliff or defend the road. Does that make sense?
Yeah.
Okay. So then once that choice has been made, here, yeah. So here it's defend. Oh, I want to get back to the color that I was using. So defend, climb, just seems like a weird word. They basically chose the correct one to defend, right? So the people climbed, Greece defended the climb, and they win, right? They get a point. Yeah. And similarly, defend road, they would have made the right choice here, and so they get a point. However, if they didn't make the right choice, we are now back to, and by the way, Greece did this with a 50% chance, I think, right? 50% chance for Greece. So now the next part is we need to, Persia it's up to Persia again. So we have, what color was that? Okay. So they can either, now we're back on player one. They either ambush or they attack, right? And maybe I'll stay on the top section. So they will ambush with a 1/3 and attack with 2/3. And oh, whoops, this is the wrong. Oh no, I did it wrong. I'm very sorry. This is actually not Persia making the ambush or attack. They're just going to just chill, and it's up to Greece to like catch up to them. And so now Greece will either ambush, right? We're back at the player two. Greece will either ambush or they will attack. And they put 1/3 and 2/3. And once again, we get to this point where we have to make a simultaneous decision, because at the same time as Greece is deciding to attack or ambush, Persia is deciding whether or not to withdraw by day or wait for the night. And so they have the corresponding points. So if they withdraw by day, then they lose when the ambush happens. And if they wait for night and the Greeks attack, then it's, I guess, equal. But if they withdraw by day, then they win. So yeah, does that make sense?
Yeah, so it's like them resting.
Exactly.
If they do rest, then they're gonna win a fight they're withdrawing. So I'm not really sure what the Persians' intentions here are. I mean, if we're following the narrative, like the Persians are invading a Greek city.
I think that they're like moving on to Greek territory, like on their way to like destroy Greece.
But in either case, I mean, if they are not destroyed immediately, they arm and then they withdraw. I guess they realized that it was bad vibes in the Greek territory.
I guess so. Because the Greeks in this case are very good warriors. I think there was something about like the Persians like gaining reinforcements or like arming themselves because they need the right weapons to fight the Greeks or something. I don't know, something like that.
Okay.
But generally this is like how it works. And now so it's like game theory turns into art of war and everyone's happy.
Yeah.
So does that make sense to everybody? Okay.
Yeah, I just have a question. What do those numbers with the semicolon mean? Like 1, 2, 1, 5, and so on.
So I think this is let me actually go to this one. So this one right here, the one right here, is the player, and then the 2 is the index of that particular choice, I believe. Because I think it goes like, you see it's 1, 1, and then it's 1, 2, and then 1, 3.
Oh, it's
right?
their moves. Okay.
It's their moves. 1, 1,
Okay.
3, 1, 4.
Okay, sounds good. All right.
Cool.
Thanks.
And it gets really intense. That's what this is supposed to show. And so basically, this is the submarine. This is like this is actually a really cool example, where it's like what's the game, Battleship. So that one's cool. So this is just a random term that maybe is important, but I don't know. It's called perfect recall. So what we've assumed in each one of these games, right, is that if we are at this point, like if we're at the final point, right, or if we're making this choice, that we remember all of the choices we made up here. And that's kind of necessary. Otherwise you may not make the best choice. And so they just say, like, keep that in mind. If it looks like this, then it's not perfect recall. But they didn't say anything more. Yeah. So, the problems I think are pretty simple. The last thing is just like backwards induction. And there's just one thing to note here is if you go backwards and you choose the best strategy, then you can actually find a particular Nash equilibrium, which is, I believe, the rational equilibrium. Let me find where it actually, reasonable Nash equilibrium. Picks out the reasonable Nash equilibrium. So like, for instance, this one, right? In each one of these cases, we choose this one. I guess we're doing it for player 1. So like 7 is better than 4, so we choose 7, and then you know, 4, and then so we like can reduce it to this path, and similarly we can reduce this to the 8.
Yeah, with
8.
perfect information, it seems fairly straightforward to figure out your optimal strategy. So that makes sense.
Yep. So I think that's really it. I didn't quite finish this section. Oh, because they're like this part, like sub game, perfect equilibrium. I didn't finish that. But yeah, I think that's mostly it. It was a pretty simple chapter, pretty short and straightforward.
Nice. So I guess it illustrates how the combinatorial explosion just happens when you have sequential games, especially if they're perfect information, because then everything is you're gonna have so many strategies available to you. Like if there are 3 moves and you have 3 options each, then I think it's 3 to the power of 3 or whatever it's gonna be.
Yeah, it's nuts. And I think that's kind of what they said. They were like, I think they said that you, in some way, you don't, like, this is such a problem just that you kind of want to limit your games so that you don't follow paths that are just simply ridiculous. You know, like you stop at a Nash equilibrium. If you already hit something with like if you do that backwards Nash equilibrium stuff, and you know that there's a path that just no one would ever choose because it's like you're an idiot if you chose it, then you just cut it off and you like can prune your tree.
Yeah, so you prune your tree with strictly dominating strategies, or like strategies that can be dominated are pruned. That's cool.
Yeah.
Nice.
It was amazing to not do solve for Nash equilibrium / find, like dominated strategy, like just not looking at those matrices. Oh, it was like the most amazing chapter.
Yeah. Yeah, nice. Yeah, it's a cool chapter. I mean, it doesn't seem like it gives, as you say, much new material, but like it provides a nice intuitive picture, I think.
Yeah, I agree. Cool. So, Tiba, do you have any questions?
Not really at the moment. Maybe you can try some of the exercise that are at the end, or do you feel comfortable doing that?
I mean, I feel comfortable with a lot of things. That should be fine. But I mean, I don't think I'm going to do it right. But I'd love to. Let me see. I think here. So let's do one. Oh yeah, this one. Oh God. I'm too lazy to do calculations. It's so bad. So I don't know. 4.3 seems like a good one.
Yeah, at least A for B.
Yeah.
We don't really have Gambit yet.
Exactly. So
But it would be cool if we all got Gambit and started experimenting with that.
I really want to do that. I'm very excited by this. Does it cost money or is it free?
I think it's open source.
Awesome. Yeah, I'm gonna do my whole screen, just so that we'll have more space.
Yeah, it's GNU, GPL.
I don't actually know best way to like draw because we just don't have.
Maybe we can just draw on the screen.
Okay. Um, so
Is that a 3? Is it oh, it's a 3. Oh, cool.
whoa.
So we have a 3-dimensional matrix. That's nice.
But it should be easy to draw, right?
Yeah.
If like, because we would still start with player 1,
Mm-hmm.
right? And player 1 can either choose up or down.
Yeah.
Okay. So I'm just gonna write a 1, and then player 2 can either choose up or down. Do you think these colors are gonna make it more or less difficult to understand?
I think it's gonna be fine either way.
Okay. So this is player 2's up or down choice, right?
Yeah.
And then we just have player 3. Player 3's up or down choice. Oh boy. And so would this just I guess these are all the, yeah, this is easy. Nice.
Maybe we'll just do this. Let's give these guys letters. And then we'll attach the letters.
Yeah.
Different things.
I think it would be cool if we found the Nash equilibrium doing the backwards thingy.
Oh yeah.
Oh, but does this assume something about which order they, oh, it's all chose simultaneously. So I totally, my diagram is all wrong. It's hilarious.
Oh, but you're just gonna add some points to it.
It's the worst color. Oh, whoops. The yellow is the dotted things.
Oh, that should be D. Yeah.
Okay, cool. Awesome. And so actually for this, I don't even know what the how would we find the Nash equilibrium for this using that tactic? Like, does it even work when it's all simultaneous?
Yeah, because we still have a matrix. I mean, I don't think we can use that backwards recursion tactic thing.
Yeah.
But we can still consider the matrix and see what the Nash equilibrium is. But it looks like it's going to be
A long, difficult journey.
something.
Yeah.
in mixed strategies.
Yeah. Okay. Yeah.
Yeah, I wonder what those fractions are. They're not entirely straightforward. But
Well,
so we should be able to solve this algebraically. It might be a bit intense.
yeah. I think we've only done 2-player games, right? So
Yeah, we
far.
have.
So I think it may be a little bit too difficult, but at least I mean we know the general structure. It was a pretty simple formulation. Do you mind if I erase our beautiful work?
Yeah. Oh, I don't mind.
Cool. I don't know if there were all that much. There's really not that much in this chapter. There's some stuff here probably. I didn't actually read it, so maybe I should. Like this is it's the ASIN2 thing.
Oops.
But we're relatively good on time. Do you want to? Should we just figure out what we're doing next week and take on chapter 5?
That sounds like a good plan for me.
Awesome. Yeah, me too. Cool. So, are we good for chapter? There were 2 sections left in chapter 4, or maybe 1 section left. I think it was one. Oh yeah, there was 1 section that was around using the Gambit software, and the other one was about the Subperfect games thing. So maybe it makes sense to at least for some time next week, just like have installed Gambit and actually compute these on Gambit.
Mm-hmm.
I feel like that would be a lot of fun.
Yeah, it definitely can be. That sounds cool.
Cool. So definitely Gambit, and then if if you do some of chapter 5 because you just can't stay away from game theory like the rest of us, then it'll be okay. And next is N-person zero-sum games with the continuum of strategies, which is exciting. And then unbelievable, it's going to be incredible. Chapter 6, cooperative games.
Oh, nice. Yeah, cool.
So
yeah, it seems like the first 2 sections, at least of chapter 5, are seem fairly cool. I don't know if they are, but I think we should have those in our crosshairs as well.
I agree. I liked our pace. We've gone through 2 chapters in 2 weeks. It's felt great.
It was pretty awesome. Cool. Then let's say that for next week.
Awesome.
All right. I'm going to try catching up with the first 4 chapters, but I think that's going to be fine.
Yes, please do. Game theory is life. All right.
Yeah. Cool. All right. I'll see you guys then. Thibaut, if you want, we also have a study group on linear logic.
Okay.
Which
when's that happening?
It's happening on Tuesdays.
Okay.
Are we doing it usually 5 CET on Tuesdays?
Okay.
Yeah. Is it
1 o'clock for you?
Yeah, I think so. Or no, 11 a.m. Might even be 11 a.m. for me. Like 15?
Yes, 11.
15. Yeah.
No, 11 is 17, so that makes sense.
Oh my god, I keep doing that.
Yeah. So the reason why people are interested in linear logic for different reasons, but it has a particular connection with blockchain, as you're dealing with resources in a fairly explicit way, and so you can have types in your programs, just as you have the type of integers and then the type of strings and so on. You can have types that are linear, so you can you can force them to only be used once in your functions, and so that way you can make sure that you can't like duplicate money and stuff like that.
Cool. Can you share resources on that, or is there a channel on the hub?
Yeah, there is a channel, and I'll link to the lecture series that we've been following.
All right. Sounds cool.
Cool.
Awesome.
All right.
All right.
Thanks, guys.
So you guys.
Thank
See ya.
you. See ya. Bye.